look at slope at a tangent line. So what if I were to address a question this way? Find the slope of a tangent line to the given graph at x equals 2. So that's my question. Then how would you be able to answer that? So let's see, x equals 2. In this case, the function that's given is y equals x squared. So we know that when x equals 2, y value is 4, right over here. It looks pretty straight, but you know that it's not straight, it's curved. How do you find the slope of the tangent line? So if you to think about it, I need to draw a tangent line very nicely. So if it's, this one can be tangent around like 1 point something. Maybe I just, something like this, okay. Something, it looks like it a little bit, but I'm not sure. It's pretty difficult for me to find. You know, it's kind of difficult. One way that I can do is maybe I put one line over here and then try to measure the, you know, slope of the line, you know, as it goes up. I don't know. Maybe one thing that which we can do is this. Let us say this is a another particular point, and then x comma y, and this x is the other point. The other point is keep on going closer and closer to the red line, which is what, 2, a red point, which is when x equals 2. When that happens, we can say, maybe it is, you know, I'd be able to get more instantaneous rate of change or slope, not between these two points, which creates a secant line, but more of the tangent line. So what I'm trying to do is, I want to find out the slope, which is y minus, in this case would be 4 because y value, this is 2 comma 4 right over here, over x minus 2. And then as these values approach 2 comma 4, we'll be able to find the slope not between 2 points on the graph, but about 1 point. So in other words, what I'm trying to do is maybe limit of the function minus 4 over x minus 2 as x approaches 2. This should be able to give me the slope of the tangent line. So then, okay, let's try to look at this one. So what I'm end up getting is f of x in this function is x squared. So what we can do is limit of x squared minus 4 over x minus 2 as x approaches 2. And as we have done this one earlier in the previous sections, this can now factor. So we get a limit as x approaches 2, x plus 2, x minus 2, all over x minus 2. And you get to realize that x minus 2 cancels away. So we are left with x plus 2. But as x approaches 2, we realize that the answer is 4. So in fact, this is how you can find the slope of the tangent line when about a particular value. Assume another point on the graph, and you are imagining as the second point is coming closer to our targeted value, which is 2 comma 4, and then we are observing the change of the slope, and we realize the slope is now approaching 4 as the green point approaches 2. All right, so let's do another example then. How about this? What if I were to say y equals 1 over x, and then we know that graph looks something like this. And then how about at this point when x equals 2? We know the y value is equal to 1/2. What is the slope of the tangent line when x equals 2? So then we're going to use the same thing. Limit of f of x minus, this is y2. y1 is when x equals 2, we get 1/2 over x minus 2 as x approaches 2. Then in this case, what I'm going to do is I can rewrite this one as limit 1 over x minus 1/2 over x minus 2 as x approaches 2. Now, we end up getting a complex fraction. So when you plug in 2, then you get 0 over 0, so I gotta do something. Once again, coming from the previous sections, I can multiply by common denominator, which is 2x. Then what I'm end up getting is limit as x approaches 2. Well, when 2x is multiplied to 1 over x, we are left with 2. And then 2x is multiplied by 1/2. We are left with x over x minus. Notice that I'm not multiplying the denominator because it's nice already factored. So when I cancel these two things away, I'm left with -1. Then our answer is -1/4. The slope at this particular point is -1/4. All right. So in fact, that's what we can do. But what if it wasn't a particular value? What if we want to make the constant? What if we want to generalize this formula a little bit? So as of now, slope at x equals a, we can write this one as limit of f of x minus f of a over x minus a as x approaches a. That's one way for you to write it. But another way for you to write it is this. Imagine the first point was x comma y, and second point, or maybe x comma f of x. Second point would have been x plus h. So it's a little bit different. It's greater by h. Whether h is positive or negative, we don't know, but greater by h. And then f is f of x plus h. So that's another perspective where second point is based upon the first point. Only difference is a difference between those 2 points, which is h in x values. Then what we end up getting is limit of f of second point x plus h minus f of x all over x plus h minus x as x approaches 0. I mean, no, not x. H approaches 0. As h approaches 0, what that basically means is that the second point is approaching the first point, just like what we have done earlier. The second point is approaching a. In this case, these two are approaching x. But we get to simplify the denominator here. X and x can cancel away. So what we end up getting is f of x plus h minus f of x over h as h approaching 0. And this is the famous difference quotient, limit of the difference quotient. And we call, in fact, this one as a derivative of f of x. Sometimes we use symbol df over dx, the change delta f over delta x, change of y over change of x, same idea, right? Or we can write it as f prime of x. Alrighty. Knowing these, then what we need to do is this. We need to figure out, we should be able to, find the derivative or slope at a particular point in 4 different ways. So first case is f of x is equal to 2x squared, just polynomial. And the second case will be f of x is square root of x, radical. And third case is the complex number, the complex fraction coming from the fractional relationship. The last one is a trig function. So we'll do first number 1 and number 2 here. So to find the slope of function f at any particular point x. So that means I'm looking for df dx is the limit of f of x plus h minus f of x all over h as h approaching 0. So what I'm getting is limit of 2 x plus h squared minus 2x squared all over h as h approaching 0. I understand I can factor the top and then try to calculate the values, which is much easier, but I'm just going to expand it anyway. Because in that way, it might be a bit easier for you to do cubic or quartic or any other functions. In fact, even if it's cubed still, you can factor that nicely. But anyhow, limit as h approaching 0. Here we have 2x squared plus 4xh plus 2h squared minus 2x squared all over h. Then you can see that this cancels away with this one. Then here we have 3 terms, and then we realize that h is common in all of them. So h is cancelled away. So we are left with limit of 4x plus 2h as h approaching 0. Then we get to realize that 4x is the only one that survives. Alright, so in case of a polynomial function or any functions that resemble something like this, we can just apply the difference quotient and then expand it. How about the second one? What if we have a radical? So in this case, limit as h approaching 0. I'm just going to skip first step, x plus h right away, minus square root of x over h. Now, in this case, the way that I can approach this one is I want to get rid of these radicals. The way which we can do is by multiplying top and bottom by its conjugate. X plus h plus radical x, x plus h plus radical x. On top, what I'm end up getting is these difference of squares, and then squares canceling away the radicals. So we get x plus h minus x. And denominator, I'm going to just keep it as it is. H times x plus h radical plus radical x. Then you can see here that x is cancelled away. Then h is the only one that's left. So h also cancels away the denominator. So what we end up getting is limit. It's 1 over radical x plus h plus radical x as h approaching 0. Then first term, if this one becomes square root of x, adding another square root of x, we get 1 over 2 square root of x. That becomes the slope of the function radical x at any given point x. All right, let's look at the third case then. Third case is what if I have function f of x is equal to 1 over x. Now, in fact, for this one, I'm going to skip it a little bit because I'm not sure if you noticed, I already have done it. Earlier in this case, all you have to do is multiply by the common denominator. Why don't you do that yourself? I'll let you know that df dx, the derivative, which is the application of limit, it should be equal to negative 1 over x squared. That's what you should be getting. But I'd like to talk about fourth one. what if f of x is equal to sine of x? Then in this case, what we can do is limit as h approaching 0. We have sine of x plus h minus sine of x over h. Now, wait a minute. We know the sum rule for sine. What is that equal to? That's equal to limit sine of x cosine of h plus, it's the same thing, so cosine of x and then sine of h minus sine of x over h, h approaching 0. Now, the way which we can simplify this one is through factoring, and then I'm hoping that you notice that sine of x and sine of x is common. So I'm going to combine those two terms. So how will I be able to do that? So limit sine of x, then we have cosine h minus 1, and then plus cosine x and sine of h. Now, since h divides the whole thing, I'll say h divides this one, and h divides this one. I just split it into two different sections. That's h approaching 0. And you get to realize that as h approaching 0, this expression, in fact, becomes 0. And you can sketch that with your graphing calculator. And then, in this case, sine of h over h, this one becomes 1. So therefore, our final answer becomes simply cosine of x. It's kind of cool. All right, so with that one, I'm going to close up. I'll see you later.